Hello, ladies and gentlemen. My name is Zhang, and I come from Nanjing University of Posts and Telecommunications. The paper I want to report today is High Spatial Resolution, a remote sensing classification with light-white CNN using Dilated Convolution. Next, I will introduce this paper from 6 aspects: background, related work, system model, DCLW method, results, and conclusions. The first is the background part. In recent years, CNN has been applied to the classification of HSRS imaging sense due to its powerful future extraction capabilities. As a result, CNN has achieved amazing results in the fields of HSRS imaging classification. Although the average accuracy of classification is high, the CNN network model generally has redundancy and takes up a lot of memory. This often requires powerful GPU and data center. At the same time, as large scene with small lights and nodes are considered, reducing their storage and computational costs becomes critical, especially for some real-time applications. Deploying deep learning systems on portable devices with limited resources is a problem worth studying. In this paper, we proposed a lightweight CNN combined with dilated convolution for high spatial resolution remote sensing classification. Lightweight methods based on deep learning are generally divided into 5 categories: parameters pruning, parameters codification, low-rank factorization, compact convolution kernel design, and knowledge distillation methods. Parameters pruning is to reduce redundant parameters that are not sensitive to the performance. Parameters codification is to reduce the number of bits required to represent each byte. Low-rank factorization is to use tensor decomposition to estimate the informative parameters. Knowledge distillation is to try a compact neural network with distilled knowledge of a large model. Compact convolution kernel design is to design spatial structural convolutional features to solve parameters. In view of different neural network structure characteristics, some methods can be deployed to achieve a central lightweight factor on the basis of maintaining the performance of the neural network. The following is the related work part. The experimental data is 10 types of input HSRS images samples extracted from the UC methods lender use dataset, and the remote sensing image classification benchmark RSICB dataset. There are 10 types of remote sensing images of airport runway, a venue, a bridge, city building, city greenery, city road. marina, parking lot, residence, and storage. At the same time, data augmentation is to increase the number of HSRS images and also increase the difference in HSRS images of each category and improve CNN model classification performance. In order to make the CNN model training feature, the image dataset is pre-processed. Among them, the table on the right shows the different processing operations and parameters taken by data augmentation. As shown in the figure, here is the neural network structure of the original CNN. The original CNN consists of 4 convolutional layers and 3 fully connected layers. It is worth noting that the number of convolution kernels in the first 2 layers is 128, and the number of convolution kernels in the second 2 layers is 64. Followed by the 2 fully connected layers containing 1024 neural nodes and 512 neural nodes respectively. When using the parameter settings shown in the table to try and test the CNN, we electro the performance of the CNN in terms of parameter amount, memory, floating point operations, and average accuracy. Obviously, behind the high accuracy writer lies on a large number of parameters, memory usage, and calculations. As confusing matrix shows, when the original CNN was tested for classification, the average classification accuracy of the 10 types of remote sensing images was as high as 84.10%. At the same time, judging from the actual values of other parameters, the resources consumed by the original CNN are also quite huge. The following is the system model of the DCLW method in my paper. As the picture shows, we will introduce the DCLW CNN method. We use the dilated convolution DC to replace the standard convolution of the original CNN to obtain the DC CNN. Subsequently, narrow pruning method is applied for further processing to obtain the DCLW CNN. Among them, dilated convolution can expand the receptive filter, enhance filter extraction, reduces the size of the output filter member of the convolution layer. Narrow pruning can prune the redundant convolution kernels and narrows of the model. Because most HSRS images are target sense information, we will use the dilated convolution method to increase the filter without increasing the model parameters and computation. In extract more textual information of the image. Improve the down sampling rate and reduce the model parameters. In 2D, when we set the dilation rate to R, the dilated convolution can be constructed by inserting R minus 1 zeros between pixels in the convolutional kernel. The size of the convolution kernel is charged from k times k to kd times kd. In this part, we will introduce the neuron pruning method. According to the weight value of each node in the neuron network, the random nodes are determined and pruned. Firstly, we pre-train the neural network. Secondly, we calculate the weight sum of the nodes in this layer and the average weight sum of all nodes in this layer. The calculation method is shown in these formulas. Then remove random neuron nodes. Finally, we need central training structures to restore CNN performance, as shown in the figure on the right. The process of neuron pruning is used in the convolutional layer and the fully connected layer. The computation metrics of DCCNs and DCLWCNs are shown in the figure. The average accuracy rates of different DCCN are 95.0% and 95.10% and 95.70% respectively. The average accuracy of different DCLWCN are 95.50%, 95.30%, 95.40%. DCCNs and DCLWCNs have better average classification accuracy than the original CNN. Each meets the precondition of large weight processing. This part is the structure of different DCLWCN. DCLWCNs have been uploaded redundant neuron nodes and achieved central large weight effect. For them, the large weight effect of the convolutional layer is obvious, and the nodes of each convolution layer are plotted by about 50%. The larger the value of R we set, the better the large weight effect. In this part, we evaluate the effect of compression and acceleration through parameters and memory and FLOPS. Comprehensive comparison of various data. Simulation results show that the compression and acceleration performance of DCLWCN R equals 7 is better. In terms of actual storage and operation of the CN model, the memory is reduced by 85%. 0.02%, and FLOPS is reduced by 75.22%. In the end, we got some conclusion. The DCUWCN R equals C1 has comparable performance in HSRS image sense classification with 8% of the parameters, 15% of the memory, and 25% of the FLOPS in the original CN. At the same time, the classification accuracy of each table of sensor has reached 90% or above, and the classification performance is more stable. However, the difference between some sensors comes from the future information of small objects, and a larger receiving filter is not required to extract the features of some small objects. Therefore, DCCM R equals C1 does not have a relatively stable classification performance. The above is all the content for my report. Thank you very much for your attention.